Okay. Hello, welcome everyone to episode 3 of Building with Quantum Flytrap. I'm James and I'm here with my guests, Emmy and Nyan. And I teach coding online, and I'll let Emmy and Nyan introduce themselves a little bit.
All right, so I guess I'll go next. So my name's Emmy. My background was physics. I studied that at uni, but now I am in tech within a financial services. So a bit different, a bit rusty on the physics, but it's good fun.
And she's been teaching me a lot of physics stuff that I forgot.
I don't know about teaching, but just playing around with physics.
And shall I go?
Now we have Nyan.
I'm Nyan. I also have a background in physics, and I'm currently in robotics. So it's also different than what I've studied, but fun nevertheless.
And you have, you know a couple of things about quantum physics as well, too, right?
Yeah. So mostly, I did my master's with specialization in quantum physics. And my thesis was on certain qubit architectures. So the exact logic about how quantum computers work, I have not studied that part, but maybe I'll learn now.
Perfect. Well, that's
why you can teach us.
I hope so.
We got the big guns here.
Exactly.
So I don't know if we showed you the game that we're playing, Nyan. Emmy and I will both pull it up on our laptops, and we'll show you how far we got. So it's called Quantum Flytrap.
Yeah.
And basically, you go through these different levels. So we've been through the first part of the game, and actually, it's too easy for you, really. Like the first, it starts off feeling really easy, and then you go through geometry, and it's pretty easy, and then interference starts to get hard.
Yeah.
And then it goes to polarization and entanglement. So I've just done these again, so that I could play on my own laptop too. But like just like for example, like okay, this is the last one before interference. So like it's this game board, and you have these fly traps.
Yeah.
And the fly traps, they're actually just photon detectors. They're just like, they just thought it would be cute to make them fly traps. And then this one is like a photon emitter.
Yeah.
And as you can see, I was very clever here because I figured out how to put these they're called
non-polarizing beam
splitters. And basically they just split the photon into two parts, or the photon beam into two parts, and then they have different directions and phase shift. I don't know if you have ever used that thing before, Nyan, the beam splitter.
Yeah. So this looks like the Michelson and Morley experiment. And I think if you take this table and you rotate it, you can prove that the ether doesn't exist.
Oh, I read about that in a history book.
Yeah, so back in the day, people used to think that there was a universal medium that light travels through. And this experiment, if you have a rotating table, proves that it is not the case.
So I wonder what this... That was not what I thought it was doing. Let's just reset everything. Yeah. So what do you mean by rotate? You mean like spin it, basically?
Yeah, I think this entire setup was put on a spinning table, like back then. But I'm not sure about the details of the experiment. But this does look familiar.
Right. Yeah, I've heard about... I think I heard something about that as well. And the idea is that it has something to do with the fact that the photons arrive at the same time,
Something like that, yeah.
even though it's spinning. And that showed something about how basically everything is relative in the universe, and if you're going at like and there is no frame of reference, basically. There's no single frame of reference, something like that.
Yeah. Yeah, so it was also, I think, part of the basis of Einstein's theory of relativity when this was found out.
Was that before?
This was before his theory, yeah.
Okay. So that was one of the things that inspired him,
Think so.
along with the guy that he saw fall off of a ladder.
I don't know about that story,
I
but
haven't heard about that one. I haven't heard about that one.
No, it's like one of the funniest quotes from Einstein. He was like, one time I was daydreaming at my desk, and I had a really happy thought. I imagined a guy falling off of a ladder. That's how he started, and then it ends up as a happy thought because it led to him thinking about how the guy who was falling wouldn't feel the acceleration, something like that.
I think more generally an elevator an analogy is used, but
haven't heard of the guy falling off, but it
no,
does.
me neither.
So yeah, fun stuff to think about when you're bored. So this is just like the last one that's about geometry, and yeah, it just shows that how the beams get split, and that obviously. So actually, I figured out you can go through, like, with the arrow keys, you can just go step by step, and you see, yeah, right. So you see how, like, it splits up into, and you can sort of like put your mouse over it, like this, and so you can actually see. I found out that if you click color over here, you can see that even though these two, so it's not two photons right now because you cannot split a photon into two photons, right? But it's
probability.
It's a chance. Oh, that's why they're faded. Okay, that makes sense. So it's a chance, right? And then this. Oh, that also explains. Okay.
It is a superposition of two states.
Yep.
Got it. And so one of them, I found out if you put your mouse over it, you can see the phase actually, which was really confusing me. I didn't understand that the first time we played that, but here you can see the phase is green, which just means zero phase shift. And you can see here, if it goes straight, it stays green, and then if it gets reflected, it gets this is like a quarter phase shift, the blue.
Oh yes.
So that helped me to understand. That was what I didn't understand that helped me to understand the next part, which is interference. Because if two of them are different phases and then they hit each other, then obviously you have the interference. If that makes sense.
Yeah.
Cool. So I think we'll probably whiz through the rest of it. Should I do it on my computer?
Yeah, go for it.
Okay. Cool. So we've done this before. I don't remember it.
So this introduces the mines, doesn't it? Like the black mines.
Yeah.
Which what did those represent? I can't remember.
It's representing a mine.
Oh no! It was the
Elitzer Weidmann bomb
tester.
Bomb tester, which seemed like a really useful device to have in your laboratory.
Never heard of this.
I didn't hear of it until this game, so I learned something new when I played this.
Yeah.
So this was basically showing that if there was a chance of something happening, it will happen. I think that's how the psychology of it worked.
Interesting.
Where if there was any probability of a photon hitting the mine, it would hit the mine.
Okay.
That was the weird.
But here they say that they can verify a bomb is functional without having to blow it up. That seems
So
highly theoretical.
But Emmy, what you're saying sounds like Murphy's Law.
no, it does sound like Murphy's Law, but I think that was the logic that we used to.
Right.
Maybe I'm wrong. I could
So
be
in
wrong.
in the game itself, basically the bombs just blow up, even if there's any chance of. That's what it seems like.
So I guess Murphy's Law is basically another flavor of this elixir Weidmann.
Let's see. So if I just go like this,
yeah,
it blew up. Maybe we're overthinking it.
So we need to change the. What do we need to change? What can we change?
Oh yeah. So Nyan, these ones are the beam splitters, and these ones are just mirrors.
There are two mirrors below your.
And these are the ones that we can move.
And the goal here is to get the light to the detector.
Yes.
So
and you have to use all the elements.
You don't have to, but normally you do have to. Normally they're all needed.
No, I think so. I think they place all of them to be used up.
Yeah. So this one I don't think is. Oh. Yeah. So this one. So basically, if we just go through it without placing any elements, so you have the superposition, and then that converges. Is that the right word? That
constructively interferes, I think.
Oh yeah. That was it. I learned that last time. So yeah, then these will just.
Yeah, I'm guessing two mirrors then to the right and top.
Mirror. Yeah, this doesn't seem too hard, right? Okay, and then you can just play it like this. You can play it fast forward, or you can just skip through the whole thing. Okay.
Yay.
Cool. So
the rock we just need to move the rock out of the way.
We can only move the rock. And the way I read this, 25%, 25%, that means that, of course, that the beam can be split twice, maximum. Well,
yeah, but now you will get, I think, one wave.
I think you'll only get one at the bottom detector, because the initial momentum is from the top to the bottom. It's vertical, I think.
Yeah, I remember that too. How would you explain that, Nyan?
Well, it's just Hamilton mechanics, right? You have starting energy and you have ending energy. It has to be the same.
Right.
Yeah.
Because here it's split. And then you have interference. And so you're saying that the energy is just the direction, is related to the direction that's going in, right?
Yes.
Yeah.
Okay. So
your initial energy will always have a position and a momentum.
Always have a momentum. So the momentum is, but so when it's when it's going horizontally, you can't see that it has that momentum, that downward momentum.
No. Yeah, exactly.
Not from this visualization.
But you can see it from the second component, which does hit the mirror. Yeah. The downward.
It is an interesting point, James, because where does some momentum does get converted, right, by the first or what you call it, the blue one,
the beam splitter.
Yeah, meaning your initial energy state is changed. So there's no conservation there anymore, I think, because you have an extra component. Or well, I'm guessing the energy can still be the same, but your momentum is not, because that's a factor.
The total momentum would have to be, but
Yeah.
it's the total momentum including the phase shift. Rather, like, yeah, it's the same energy. Yeah.
So
the total momentum in the same direction is not conserved, so downwards.
oh, so I was messing with this, and this is kind of what I saw is like, if I block this one here, for example, now of course it's not gonna interfere, so it will split here. And then what I saw is that the phase shift is now green and blue. And the green, and like, I don't think that's like actually a physics notation, right? They just made up for the game, right?
The green and blue, yeah.
but that means 0 and 1/4. No, sorry, 0 and
Yeah.
0 and 1/4. And then if you actually go back here, you put it here. Now I let it split again. Now it's pink and blue, which is and the pink is 1/2. Is it 1/2?
Pink. I don't know what the starting position is.
The starting should be green, because here you go back and it's green. So then you have.
Okay.
So there's I guess what I'm trying to get at is that there's a phase shift going on. So like this one is the same as the initial. This one is shifted. And now this is shifted. So I was thinking that basically
it's a clockwise and anti-clockwise shift.
Yeah, you have one that's clockwise and one that's anti-clockwise, and that this bit here would get canceled out. Basically, would destructively interfere. But just this right direction component. Does that make any sense? That's the way I was thinking of it. Is that like,
how much percent did you get when you put the rock there at the detectors?
Where should I put it? Here?
Yeah, for example.
So if we do this, it works.
And
that makes sense.
Initial state, did it not work then?
So
when the
if
rock
we do
was
the initial state, it can't work because we don't we never get anything on this side.
I thought the initial state was when the rock was in between the.
No, it was here.
Oh, okay. Yeah.
So, yeah.
The reason why it splits into 25% in each detector is because you're blocking off one of the light pathways, so therefore there's only 50% total.
That makes sense.
The other 50% gets absorbed by the rock.
That makes sense. And if we do it like this, you get 100%.
Yeah. That's so interesting.
So this is the okay, but still, explain to me like I'm really dumb. Like, is there a way to how do you predict that it's like, how do you predict step by step that it's only going to come out the bottom and not the right?
So I think you have to take it at each point of change or observation. So, i.e. the first beam splitter, it's going to split 50%. There's a 50% probability of it going one way and 50% probability of it going the other way.
Okay.
And then from there, you know that when it hits the mirror, it's going to reflect at the same probability because mirrors don't change the phase.
Yeah.
Then when they converge, they're going to constructively interfere. So you're going to have 100% of the light at the second beam splitter.
Yeah.
But then they're going to split apart again because they've hit a beam splitter.
Mm-hmm.
Or rather, they're not going to split apart because the probability, actually, they will all go downwards because the downwards momentum of the incoming vertical component will mean that it will constructively interfere, whilst the other sideways particle,
that's this one.
the probability will reflect.
Oh. Because this one going down, it splits into this way and this way. And this one goes into this way and this way.
Yes, so I guess it destructively interferes with the horizontal component, and then it constructively interferes with the vertical component.
Right.
And so the overall effect is that there's a downwards component of 100% probability.
Okay.
I think.
One thing I am wondering though, does the phase change over just space alone? So if, for example, if you move one step back, does the wave have a different phase than if you go forward in time?
It looks like no, because the phase shift is this part.
Okay.
Color part. But here they do actually switch. Looks like. I think because this one is blue. Oh no, it stays blue. Never mind. It just changed the order.
Oh, okay. Yeah.
But and it's also possible to look at it like in these other
coordinates.
Notations, but I don't know which one. I don't know what would be normal polar.
Yeah.
I guess so.
And then what's in the exponent is the phase.
Yeah.
Oh, here.
Yeah. So you have the amplitude in front of it, and then the phase in the exponent.
Oh, okay. So here, it's not shifted. Here, it's shifted.
Yeah, to half pi.
Okay.
Then back to 0. So
back to 0. Oh, actually, here it's still shifted.
Half pi, right?
Half pi. Yeah. That is half pi, which is 90 degrees.
Okay. So here, if I block 1, then we have one that's half pi and one that's pi. But if I block the other one, then we get one that's 0 and one that's half pi. So the one that's 0 and the one that are pi are destructively interfering?
It's a minus sign, right? Exponent with pi, that's -1.
Yes. Yeah, you're right. E to the
So
pi.
the amplitude is exactly flipped, meaning it will destructively interfere.
Oh, you said it's minus pi.
Wow, I have not done this in so long.
Here, this one. So e to the pi, it's exponent of pi times I.
Yeah, so that's Euler's formula.
Yeah.
That's -1. So the amplitude is -0.71.
Oh, it's -1. Okay. And if we do this way, it's...
Well, 0 is just 1, right?
It's 1. So then the amplitude is 0.71. Then you add those up, and then it cancels out.
Yes. Because you have -0.71 and you have 0.71. So that's the maths behind it.
Yeah. If the states are the same, it's just additive. So you can just add the one amplitude with the other one.
In this case, because you have plus and minus 0.71, they cancel to 0.
Yeah.
Interesting. Okay.
Ooh, I finally understand how these notations
So, yeah.
That
makes sense. That makes a lot more sense than it did last time.
Nice. I also found the colors to be confusing.
Yeah. These colors.
Yeah, I those are really weird.
It it helps me.
I think it's trying. It's like a good color key,
It's
but
like
you need to know the maths before you know the colors. I think.
I was more the other way around. I was like, oh, pretty colors. But yeah, it is really amazing that they have figured out a way to display. Anyways,
Nice diagram.
yeah, right. Anyways, that helps me a lot. Thanks, guys.
I think a lot of that was credit to Nayan.
Thanks, Nayan.
No
Thanks.
problem, I guess.
Ready
Can
for
you
the
try to put the rock anywhere? So
here?
after the first splitter on the right.
Here. Yeah.
Will anything work? So if you now put it,
Here?
on the bottom row maybe. This one you tried already.
Here?
Yeah. Okay.
Oh,
anything will work.
Makes sense.
Then.
Yeah, and that does make sense if we go back to Emmy's explanation of momentum. Like, well, no, actually, that one doesn't.
Yeah.
Okay.
No, it does, because 50% of the light is blocked by the rocks, and then the other 50% is split into another 50% by the final beam splitter. So.
Right. Yeah. But yeah, it does make sense to me that basically one component of this cancels out the component that's coming the other way. Okay, so it's basically like two, would you say, entangled states that are interfering with each other?
I just say interfering.
Okay.
Because entanglement is slightly different. Right, Nayan?
Yeah.
Yeah.
It's a superposition of two states.
Yes, exactly.
That are interfering with each other.
Yes.
Okay.
Which is like the double split experiment, right? You can send a single electron, and the single electron can interfere with itself.
Yes.
Yeah, this is a lot like the double slit experiment, right? Because
That
the
one,
double slit experiment, the phase, it's really the phase that is changing for like on the different spots, right, in the screen.
Yeah.
Okay, next one.
Sure. Yeah.
Yeah.
It's actually quite a fun game.
Yeah, it gets me reminds me of my old rusty physics.
So let's see.
So this one, you're going to have 50% probability when it hits the first beam splitter. So it's the same kind of setup actually, except we need to use the phase shifters, lambda over 4, lambda over 4. So yeah, it shifts.
What do they do?
They shift the phase
by
quarter
lambda over 4, which is
quarter wavelength, which is pi over 2.
Okay.
Right.
Oh, lambda is the wavelength, of course. Yeah. So lambda is 2 pi over 4, then I guess.
Yeah.
So by half.
Yeah, pi over 2. Yeah.
Glass has a refractive index of around 1.5, meaning that light travels at a slower speed. Okay, and the thickness is set to retard the phase by lambda over 4. Also depicted as blue.
There we go, as blue.
For people like me that enjoy that color.
No, I like the colors. I just think the numbers make sense before the colors. Sometimes, depends.
It does help, yeah.
Unless you've seen all the colors and their effects. So yeah.
Yeah, it's less intuitive that green becomes blue, becomes pink, becomes orange.
No, I like it though. It's nice.
So currently you will get 50-50, right? But you want to have the X component after the second splitter to be to have deconstructive interference.
Yeah.
Right, because we want no what's the word? We want no magnitude at the end.
Yeah. So how would you cancel out? Because we have a rock and phase shifters. This is.
Oh, so this rock can't move actually.
Oh, it can't. Okay.
This rock is just spectator.
Wow. I
It
think
moves the eyes.
moves its eyes.
If you look closely, you can see there's like a little light box here that shows you can move these.
Okay.
Yeah.
Yeah, but the detectors also have those, and I don't think you can move the detectors.
Oh.
Oh, whoa.
What?
What?
I guess you can.
I was not thinking that. I don't think we're supposed to move those.
Well,
Oh
if
my
you just
God.
want 100% in the top one, just
So
just put it in front of the sensor.
yeah, but look, actually, we can't rotate it though. That's the problem.
Okay.
Oh
gosh.
Yeah, so I guess half the photons still get lost.
Yeah.
We thought we
need to channel the horizontal. We need to make sure we shift it by pi over 4. Sorry, not pi over 4, lambda over 4.
Well, you want pi phase shift, right?
Yes, we want to be able to shift the light pi over 2, I guess, in total.
So
right?
when it
You
goes,
want to have -1, right? You want to have deconstructive in the X component.
so when it goes through the non-polarizing beam splitter, one of the components ends up being not shifted at all, and then the other component ends up being shifted by, I guess this is lambda over 2.
Oh, so the splitter also shifts, of
The
course.
splitter shifts. The one that goes straight doesn't shift, and the one that gets, I don't know what you call it, deflected.
Yeah. Reflected. Deflected.
Gets shifted by I don't. What's the terminology we're using? 1/4 of it's getting by 90 degrees. Yeah.
Oh, sorry. Wait. Yeah.
Of course, the wavelength is pi over 2.
We can see that here. Like, well, now it's in the colors, but if I do polar, now you can't see everything. But if I go like this, you can see like one is there. After it goes through there, one of them is shifted by pi over 2.
So if you do a bit more forward, I want to see the left beam in the horizontal state again. So if you two more steps, what's the phase on that now?
So now now this one is, it stays the same after it goes through the mirror.
Mirror doesn't change. Okay.
Mirror doesn't change the phase.
But when it gets to the second beam splitter,
then the phase will
divide again.
I think Amy is right. I think we just want one block then.
Yeah.
Yeah, I think you're right.
Where should I put it?
Let's try. There's no harm in getting it wrong. So
I think either on the left or the top side should work.
Here, for
it
example.
make a difference wherever we put it.
Yeah, actually, you're right. Shouldn't make a difference. Now it's 50-50.
Yeah, so we need 2.
What was it before?
Oh, it was 100 on one side, yeah.
I think we need 2 on the same path, if that makes sense.
Oh, what happened? What changed between this? Then it was 100. Oh, 50-50.
We need to shift it by another quarter wavelength.
Why does it go to 50-50?
You try to explain us.
Me?
We're having some kind of interference, right?
Yeah.
At this point, we're having interference.
Yeah.
And it's 1/4 wavelength interference. But actually, I do get that, because if you would take a wave and then another wave, and you would shift by 1/4 and then add them together, you should get half of the amplitude. That I do remember that.
Yeah.
From like signal processing.
Yeah. So the reason is probably because you shift the wavelength of, but when you only had one phase shifter, you shifted the wavelength in one direction but not in the other. So when they interfered again, they caused only a 50% destructive interference at the final beam splitter.
Huh.
So instead of cancelling out, like if you had nothing there, like no phase shifter, what happened was you were seeing destructive interference in the vertical direction, but in the horizontal direction, they were constructively interfering when they joined.
Yeah, so exactly. The last splitter, if you have a beam coming from the left to the right, will let one half of it through. That will not phase shift, but the part that goes up, that gets a phase shift. And if you add that part then with the other beam that's coming from the down, then you need to take the part that's going through, so that has no phase shift, and then add them up and see then see if it becomes 0 or something else. And the same with the horizontal direction. But that one, for the beam coming from the bottom, gets an extra phase shift because it's, I think, reflected.
Yeah.
Shall we try it?
I think we can try to, before we simulate, we can try to think if this makes sense.
Okay.
Maybe.
Sure. What if I walk through it?
Yeah.
So in the next step here, they will shift. The one going straight will not have a phase shift. The one going up has a phase shift now.
Yeah, so it went from half pi to pi.
Yeah.
And now it's at pi and a half, as I think you call it.
Yeah.
1.5 pies.
3 over 2 pi.
I think this will not work. I think the light will not arrive at the place in time. Maybe. Can that be?
No, I think it was.
I guess they put a refractive index then there for no reason, but I thought maybe the light would be slowed down or something because it was in a medium, but I guess not.
Interesting. But I guess because we're measuring such short time scales.
Yeah, could be. That's also true. Light moves very fast. And then it works.
There we go.
So here, this one is shifted by 1.5 pi. This one is not shifted. Comes through. Now we're at 2 pi. Well, at least in one direction in this direction we're at 2 pi, and in this direction we're at 0. Probably, right?
Well, so the top beam, what phase does that one have? The one going horizontally?
1.5 pi.
Yeah.
And this one has 0.
0. Okay, and that one gets reflected I guess that gets half a pi less phase when it goes to the right.
Right.
And then 1.5 pi plus minus half pi is
going to be 1.
Pi. Yeah, so and pi is minus 1, I guess, but that doesn't add up because.
So
no, I did it wrong. You don't add the phases and then do the exponent. You do the exponent and then add it together.
Yeah.
I did it in the wrong order.
Yeah. So exactly. Do you want to do it again?
Yeah. So you have 1.5 pi. That will stay 1.5 pi.
This one.
What's that? 1.5 pi. It's not 0.
So you want e
Is
to
that going to be
1.5 pi?
Yeah. e to the 3 over 2 pi.
That is 0, right?
Oh, e to 3 over 2 pi I, isn't it?
Yeah.
That's minus I, apparently.
Minus.
Oh,
Oh, yeah.
of course. Whoa.
Man, I'm so rusty.
No, I'm really rusty.
How do you say it?
You
How do you
still
say
are.
it first? Is that something everyone knows, except for
Huh?
me? Is that something everyone knows except for me?
It's the unitary circle, right? It's
Yeah,
it's just
Euler's
yeah.
equation.
It's like the first thing you learn when you go to uni. It's in the first
Yeah.
bachelor course. They're like, here, this is the unitary circle.
Okay, so, yeah, it's the first thing you learn with imaginary numbers, right?
Yeah.
Yeah. Wow, I'm rusty.
I'm in the same boat. It's okay.
Okay, this thing.
Yeah.
Exactly. That's Euler's theorem. But basically, if sine is, well, if we have 3 over 2 pi
Here, I mean up here.
Yeah, you go to you start at 1, 0, so exactly there, and then 1.5 you get to
here.
Yeah.
So I end up with minus I as the amplitude.
Yeah, times whatever was in front of there. So I'm guessing.
Yeah. Yeah, times this, times 0.7. And then, so that's the right direction component. And then this one is at 0, but it should get shifted probably one half pi in the other direction, like counterclockwise.
Yeah, so the structure of the interval.
And then that would make that would make I.
Yeah.
That would be e to the 1/2 pi times I.
Yeah.
E to the pi over 2 is I? E to the...
Yeah, it should be. E to the pi over 2...
It's 90 degrees, so it should be I.
Yeah.
Okay. Well, this is exciting.
You're starting to understand, which is nice. And I'm starting to relearn things that I should know.
No, same. Gosh, it's been ages.
Interesting. Yeah, I always thought imaginary numbers were made up for, but there's something real about them.
Quantum mechanics, unless quantum mechanics is made up.
So yeah, that one destructively interferes, and the rest has to be here. So, shall I?
Yeah.
Okay.
There we go.
It gets harder.
Yeah, I guess if we were to break down every step, the more you look, the more you learn.
Yeah.
The deeper you look.
So let's just see where we are. Like, oops, I think we got to 13. There's a lot more in this level. We don't have to finish this level today, but maybe we'll see.
Oh, this looks a bit more complicated. So everything should end up at a detector.
It all has to end up here.
And there are a bunch of mirrors.
I think we put the mirrors down the middle.
Yeah, actually, I think it may be easier than it looks.
I think if you don't overthink it too much.
That's how we did it last time.
Yeah, it's true.
We're like, this
go by
looks
trial and error.
But that's why I said I wanted to do it again, because I was thinking afterwards, like I was like, I don't feel so good about this. Also, we got to the last level and we just didn't.
That one wasn't. No, the last level was not.
But I feel like you could understand this one now, right?
But this one is quite easy, I think. It's just if we place them down the middle, it's because they keep converging and diverging. Yeah, I think the difference with last time and this time is that we actually understand the notation now
Hmm.
behind the phase shifts. And I think
Yes.
that really helps if we were to calculate predetermined outcome, like a probability for
Yeah.
our final level that we got stuck at.
So you're saying I should put this one here
Yes,
and this one?
at the end. The same.
That's interesting because now I'm wondering, will it go right or will it go down?
But you've got a rock to stop.
You
No,
can't move yet.
No, the rock is not helping.
Oh, no. Oh, yeah, you're right. Hang on. If we trace it through, as
Yeah.
in so the light will split 50-50.
Yeah.
It will then reconverge and constructively interfere and then split apart again with a right component, and then it will hit the mirror, and split apart again in both directions, and it will reconverge with a downward component.
How do you know?
Because when it shifts in the third beam splitter,
Uh-huh.
it shifts in the other, as in I guess it goes full circle. If we
Yeah.
consider at every beam splitter being another increment to the phase shift,
Uh-huh.
it's going to split by pi over 2, pi over 2, pi over 2, and it will eventually, is it pi over 2? Yeah.
Yeah. So here it's at the phase is at 0, the phase shadow is 0. And here it's at pi over 2.
Yeah, there's at pi over 2.
But this does mean that this whole story about energy conservation and momentum conservation is not valid for the earlier question. It was also a exercise of adding phases together.
I think so.
Because it's not conserved, right? The mirrors and the splitters, they change things. So I guess that argument doesn't hold.
Yeah, I guess so.
So you can have...
But the momentum will be the same if you add up the different components, I guess, if you ignore the direction.
Yeah, but unfortunately,
But
momentum
obviously
is direction.
Yeah.
But okay, but now my mind is blown a little bit because we have a bunch of photons that are being sent to the right, and then they all end up going down.
Yeah, it's because of the mirror, right? It
okay.
changes the direction. So
phase.
Oh, right. Okay. That makes sense because when it's split in two, obviously the momentum's not changing here because because of the way the mirrors are. But when it's here and then it goes to here, then the momentum is changing.
Yeah.
Got it. And I feel like in the earlier example, momentum was conserved because we didn't have this thing happening. Okay, that makes sense. Now it should be going down by that account.
now I'm confused, but
but like,
no, I get your explanation. I'm just still thinking about the last case, like
which one? This one.
the one we started with, I think.
This one.
Not it was this one, right?
Where we
No?
Oh no, the next one after this.
Okay, this one?
It's
was a different one.
Never mind, I don't remember.
Which one?
No, it was this one. It was this one, yeah.
But this is just a section of our, right? It's just the beginning section. So
That's
it doesn't
true.
hold true. It's the same laws. Where it splits.
Here momentum, sorry.
Oh no.
Here the momentum gets conserved because the mirrors are opposing each other. That's the way I visualize it.
Yeah, but after the first split, momentum is not conserved anymore, right? Because you suddenly get an X component that you didn't have before. So there is no momentum conservation.
Oh, like that.
Yeah, it's the splitter that acts on your system. So things change.
Yeah, the splitter destroys the conservation
Oh, really?
Yeah, so I don't think we should think in that
I don't think
way anymore.
Yeah, because I feel like I know it doesn't. It just in my brain it does not sound right to say momentum's not conserved.
But it's
That
like
feels illegal.
if you have a moving car and you push on it, then it gets more momentum because you're the external influence, right? It's the
Yeah.
same with the splitter. It's just something external that does something with the initial state. Which is why, yeah, sure, in total, in if you consider every single interaction, sure, momentum is conserved.
Yeah.
But if you
yeah,
just
yeah,
look at the beam, it has a different momentum when it started compared to after
sure.
the splitter.
Okay. I won't argue with this.
Yeah, I agree. No, I agree. I agree.
I'll accept this.
Completely get you.
For
So
now.
the momentum is different for each pathway depending on where the beam splits it.
Oh, we want to be. We were at 13. Yeah. So basically, the sum of all of the phase changes basically means that at this last splitter, it
Exactly.
yeah, the
There
amplitude.
is constructive interference towards the bottom and destructive towards the right.
Yeah.
Yes.
And we can see here, like we have 0, we have pi over 2, then we have just pi over 2, then we have pi and pi over 2, and now we have just pi. Everyone satisfied with that?
Yes.
Oh yeah.
Fabulous.
Okay. Oh no, this is where it got just completely. This is where my mind just completely went off the rails.
Oh, this is peeking at a photon. Okay, so this is when you make an observation.
You collapse the wave function,
Yeah.
right?
Yeah.
Yeah.
Fun stuff.
So as of now, everything will go to the right.
Yeah. So let's see. So going to the right.
Well, now I know it will split, and then all of the photons will be. Yeah. Exactly.
Right. And what do we want? We want 0.
50-50.
50-50.
Or 0. No, right? You want 50-50.
No, we want 50-50.
Oh, required at least 50. Did I read it wrong? Yeah, I read it wrong.
I think because you started the simulation, it was like. Okay,
Oh, that's that part is a bit confusing. Okay, cool. Okay, yeah, this is where you're gonna have to really explain quantum mechanics to me here, because looking at it changes everything.
Yes, exactly. So when you let me place the what's it called? The observer in anywhere after the first beam splitter.
Non-demolition photon detector.
I think what you have to do is you put after the mirror just the observer anywhere, because what that does, it collapses the wave function. So you will not be in a superposition anymore. It will be definitely on the top side or on the bottom side. And then if you have a single photon again, it gets splitted by the splitter, and then you have 50-50. So this will work, I think.
Oh.
Yeah, I think it would work at any point. Any point after the, I guess
After
after the first splitter, any point would work. Yeah.
Okay. So basically what you're saying is that the interference cannot occur here anymore at this point. Because there are no multiple components coming in together. It's just one photon going through.
Yeah.
Okay. That actually made sense. It's gonna stop making sense again later, but it's fine. So
step by step.
I don't see any percentages.
This looks vaguely familiar, but I don't.
Tuning Mach Zehnder. Oh no, this was just an experiment, right?
Do you know what Mach Zehnder is, Diane?
No.
I can't remember what this was.
Let me look it up.
The Mach Center interferometer. Wasn't it used for gravitational wave detection? I can't remember now.
I never studied that part of physics.
Determine the phase shift between beams.
Between two collimated beams. Let's see.
Measure the relative phase shift between two collimated wave beams, and collimated means parallel.
The collimated sounds very familiar. What is collimation again?
Basically, beams that have been like they're just straight.
That's the thing in the particle collider. It focuses the beam, right?
Yes. Yeah. Exactly.
Focuses the
beam. Have you ever seen one in CERN? How big it is?
I haven't been to CERN.
Well, I was supposed to go, but then Corona happened. But I saw on the picture it was very big.
Oh my god! Oh yeah. Well, the particle colliders in CERN are huge.
What's the thing called? A collimator? What is it?
Collimators are the thing that focus the beam. So it's like often, you have them with X-rays as well.
Yeah.
It's a tube basically, and you attach it onto the lens of the beam, and it just focuses the light to a singular point. So it makes it an actual straight beam. So it guarantees that the path is going to be straight.
Right. So it's like the opposite of focusing it. Really, it starts at one point and then, well, yeah, it all becomes.
Yeah. It makes the, what can I say, cross-sectional area cylindrical in that case. So it's just like it directs the beam so that it's straight.
Cool.
That's huge.
So basically, it determines the phase shift between two collimated. Oh, I turned that off.
Yes. So when you have two kind of, I guess, normalized-ish beams of light,
yeah,
you can determine what the difference between them and use it to, I guess, calibrate your two beams.
Okay, that makes sense. Measure phase shifts. Okay. So we're supposed to do that here.
One thing I like to think about is somebody designed this game. And somebody understood all of this so well.
Yeah.
Well,
it's pretty cool.
If you go to the lab, you'll see. Should I? There's way more stuff in the lab.
Yeah, go for it. They have all kinds of setups, all kinds of experiments.
Yeah, they have everything there. Every kind of. I can show you here. Look, this is the lab. And if you go here.
Oh, those are a lot more symbols. I see symbols I haven't seen. Oh.
And then they have all of these.
I don't recognize a lot of these, like the Sagnac or Deutsch Josse. Actually, Deutsch Josse? What was that? I can't remember.
C not for bell correction. Okay.
Bell creation.
Bell creation. Sorry.
I guess that's to do with Bell's inequality.
Yeah.
Yeah. So I really want to understand the algorithms, right? That's really interesting.
Well, we have courses in Delft on it. Oh wait, you're not in Delft anymore. Sorry. Sorry. Sometimes I live in the past.
Why take a course when I can get my education for free on the internet?
That's true.
I have a world-class education in front of me with YouTube.
Maybe Mayan, but not myself. I haven't known education for a bit. So
maybe you two should teach an online course.
Online course on quantum mechanics as we learn. Learn with us. Revise with us.
I can give a course in Yapaholics. That's
Yeah.
In what?
Yapaholics.
Yeah, alcoholics. I agree. I can give a course in yeah, I don't know.
Yeah, the bell inequality is fascinating to me. But anyways, for another time.
That's the big one.
Yeah, that's the one where
to prove that you have non-locality, I think.
that's the proof that quantum
Yeah.
mechanics is legit.
Clausius bell inequality. Wait, isn't it the CHS? Oh wait, what was that? Something
Yeah.
Yeah, I think it's the
CHS.
same.
Yeah. Is the
But-
same is it the same thing? It is, right?
This one, CHSH.
CSH. See how'd it go?
This
One sec,
one.
I'm grabbing my charger.
Go
Okay.
for it. CHSH. Yeah. That's the proof of Bell's theorem, which proves that non-locality. That
Yeah.
Can't be reproduced by local hidden variable. Yeah, it's the local hidden variable theory stuff.
Yeah.
And yeah, Clauser, that was it. Clauser, Horn, Shimony, and Holt. Yeah.
And these guys came before Bell, right? Or I think wasn't it Bell who? No, wasn't.
Yeah,
I think-
Bell's inequality was slightly different, wasn't it? But they work together, as in Bell's inequality. Let me search it up.
I think Bell's inequality is just purely mathematical, and the other guys were the more physics. Like they, I think, came up with an experiment or something, but I'm not sure.
Gosh, I can't remember. It's so long ago.
Yeah.
Yeah, here. The first experiment was with Clauser and Friedman. Yeah. Incredible.
Whoa.
I think the first loophole-free experiment was done in Delft, right? In 2015.
I heard about that.
And 2 years ago, I think the Nobel Prize was given in experiments related to this.
Oh yes, that's right. That's right. It was, I forgot what it was. What was it for again? That Nobel Prize.
Quantum internet or something, but that's very much related to this. It was 2 years ago when it was, yeah. I think.
Yeah, 2022. Yes.
Delft researchers teleport quantum information across rudimentary network.
Quantum relationship of two particles that can exist over long distances.
So is it basically the Bell's Bell's theorem test, but just over distance?
Yeah, so you don't have any local effects, I think.
Yeah, proves non-locality. So they experimentally proved non-locality, basically.
Crazy. Well, shall we do another couple of levels?
Yeah.
Nyan, how late is it over there?
10:30, but I don't work tomorrow, so.
Okay.
I do.
That's a fun night.
We could do a couple more, and then when we finish the section.
Nyan wants to finish it tonight.
I want to finish
Why?
everything.
Okay.
I'm engaged. I like this. I miss physics sometimes, so this is fun.
Well, you're still doing something physics-ish related, right?
I work with robots.
Robots.
Which is
It's pretty
also
cool.
cool, but
Yeah, there is some element of physics still in your work.
yeah.
Oh yeah.
Yeah. For
That's
me, there's absolutely nothing. Everyone will be like, quantum what?
Honestly, I think that if you play that, it will just everything should eventually go. Oh no, well, part will go back to the detector or to the emitter.
So we can move These ones we can move, and this one we can rotate. The one in the middle.
So if we
And-
rotate that
90 degrees.
degrees, yeah.
Oh, you want it this way?
Sorry, yeah, you like that. 108.
No, this will also not work.
So they're gonna come out of here, and we want how many of them to go into the fly trap?
I'm guessing all of it.
Hmm.
Right? Because
Oh.
I don't see a percentage.
Let's try it.
Yeah,
What?
so the
Yeah, that
ones that go to the right get partially reflected back to the bottom.
Wait, but we didn't even.
So either way.
So
We didn't do anything. Oh,
Yeah.
it wasn't this.
That's not, yeah. So either of the diagonal positions work.
I don't understand what the goal is.
Yeah, me neither. That's
I
some
don't
of these
know.
are lacking explanation.
A lot of them are lacking explanation until we figured out how to explain a few of
If
them.
I go to the lab and I look under here, is there any kind of? It just says C on Wikipedia.
Oh no.
But wait, did all the photons end up at the detector? Because if that's the case, then I'm missing something.
No, they couldn't have, right? So because this is the polarizing beam splitter, if you look at it, some of them, like when it's going to the right. Oh, actually, here they do all go back to the left. I thought they would go through. Oh, this is not a polarizing beam splitter, it's a mirror.
Yeah, so what happens is they split 50-50 at the beam splitter the first time, then they reconverge, then they constructively interfere.
Mm-hmm.
And the
but
one
it is
to the left stays and the one to the bottom doesn't?
That's really weird.
What's the question?
Why does to the left constructively interfere and why does it not constructively interfere to the bottom?
I think it's still
destructively to the
does.
left.
Does it? Wait, actually, could we play it
Oh,
very?
you're wondering if it bounces back down.
Yeah.
See, I think it does. We can do step by step. Let's see the play by play. Yeah, it's going back down too.
But then what's the point? To have a photon arrive at the sensor or?
Yeah, actually, because it shows the count of photons that arrive at the sensor. Sorry, at the, what do you call it? The source. I think when you play it through, it shows how many photons land.
And it was like 50%. If we go through like here, it's like 1. Yeah, see, then you can see
It's
how.
oh,
It's actually it should be
50%.
50.
But that's because of the distance of the Mach Zehnder interferometer. So it's the distance of the two mirrors, which are not the same.
Wait, you're saying if we change this?
Yeah.
It seems still 50-50.
Okay.
What would the distance change?
I thought it would change the frequency. I'm not sure.
It should.
Well, I think maybe it has to do something with the Mach setnet. Like part of the calibration or the tuning is to have 50% end up at the sensor at the emitter. Because let's say there was a small change in the angle, it wasn't exactly 45 degrees of the splitter, then the percentages would be different, maybe.
Yeah.
And I think maybe part of this experiment is to have your experimental setup in such a way that everything is calibrated correctly. But that's just thinking out loud. I don't know.
If we look at the actual Mach Zehnder interferometer here,
Yeah,
it's a little bit different. See?
Is this the actual setup?
So this is from the lab. They have, yeah, this is what they say is the actual setup.
I'm surprised.
Yeah.
Actually,
Why?
no, I'm not. No, it makes sense.
because here,
What is that phase shift? Very small phase shift.
yeah, it says 0, but we can change it actually.
Oh.
So let's run it. Oh, it's like this. So you have 100 here, which you'd expect because this is doing nothing. Now let's say we change this shift. Then we get less.
Yeah, that would make sense.
Change it to 1. It's at 100 again. Change it to half. Now it's at 0.
That makes sense because it's flipped by a whole 180 degrees.
Right. Yeah, no, I don't know what it is. But it's...
Maybe it's just playing around. It just
Yeah.
lets us experiment. I think that's the only purpose. I don't think there's an aim.
Yeah, well, so on Wikipedia it says that the Mach-Zehnder interferometer basically tells you the phase shift between two different beams. So here, I guess we can set the phase shift here, and then probably from this result, 0 or whatever it is, we can tell what that we can infer what this one is set to, right?
Yeah, I think so.
Right. So this one is set to like 0.25. This one comes out. So that's probably all that the device does.
Yeah, I think so. That makes sense. It's to measure the phase between two beams by measuring the probabilities of the incident photons.
Can we go forward, Nyan? Cool.
Is it the one?
Was this the hard one or was it the next one?
I think it was it?
It gets harder. This is not the hardest one.
Oh boy.
Oh, but this is the one that we stopped at, right?
Oh, really?
Was it? Actually,
maybe
maybe not.
check on yours. Check the stream. We were on it for like...
We stopped at 17. We stopped at 17.
Yeah.
Okay, so can you just play it a few times? I'm wondering what's happening currently. So they go there.
Ooh. Okay.
Okay, so we need to get rid of 75% of the beam, I think, right?
What was it initially? Oh, it was 12.
Yeah.
All right,
Yeah.
we need to get rid of, yeah.
Oh, but wait, there's the detector at the left.
Yeah, we have
No, exactly. So it needs to be like equipartitioned at the last beam into 12-12. But before
Yeah.
that, we can block some of the, either change the phase or, well, I guess you need to block it in one direction.
So you're saying to put this one here?
Maybe the rock.
Yeah.
And then you should hopefully get 50-50. But we also need to split the whole initial beam 50%.
Okay,
So-
but this does
25.
work in a way, right? Because now you have 25-25 on the
Yeah.
right. So now we just need to figure out a way to get part of the beam to the left.
Yeah, exactly. We need 50% of the beam in the left, which means we need to have a phase shift.
How did you decide to put the rock here and not the observer here?
We can try that.
This should also go to 50-50, right?
Yeah, no. Ah. Okay, that's interesting.
Yeah, but they both seem to be possible, yeah?
But my guess is the rock you put there because
I agree.
let's say you have the left part of the screen which needs 50% and the right part needs 25%.
Mm-hmm. Right.
So on the right part, we can actually lose photons, which you do with the rock. While I feel like the observer has more functions than just yeah.
Yeah, the observer actually changes the measurement.
Okay.
It collapses the wave function when you make an observation.
So
So it guarantees.
because just to confirm, if you play it now, you get 25 on both observers, right?
Yeah, we
Instead
just
of
did that.
50.
We got 25.
Okay, yeah.
So we
Okay.
need to halve that.
So
Exactly.
what if I put this here? Should I try this?
Well, think about it first because we can try everything, but I feel like we then don't
This
understand
guy.
it.
If we put it there, we're going to get phase.
No interference at the second one, I think. The second splitter.
The second beam splitter.
The interference will start at that splitter.
Right.
Yeah.
It'll start here. Oh, yes, then we'll have something completely different because then we start to use this part, which we weren't using, of the circuit, which we weren't using before.
And is there then perfect 50-50?
Basically, at the second splitter, you will have a rightward momentum. Rightward, yeah. Right.
If I put this here, then I should get half of them going down here and half of them going across, right?
I think so, yeah.
Yeah.
And then the one going across, like to the right.
Yeah.
I think we need the phase shift there then because we want to only keep the vertical component. So I think if you put the phase shift maybe either on the vertical or the horizontal one, then that should work maybe, but I'm not sure.
If you put it on the wrong one, we'll keep the wrong component though, right?
I don't know.
Yeah, you're right. You're right. Yeah. So now you put it on the vertical, it gets changed in phase twice, meaning that whatever is coming in from the other side. No, I don't know. I don't know.
No. I see. So we're gonna get this one's gonna come in from the left. It's gonna come back here.
But it's going to split.
Yeah. And this one, it gets shifted by lambda over 2, gets phase shift by lambda over 2. But then it comes back down.
If it gets phase shifted twice, it basically goes a full cycle. There's going to be no phase shift in the end.
No, but so what I'm thinking is, okay, you have the horizontal component, and when it gets back, it also gets a phase shift up, and that one that goes up needs to be compensated with the initial reflection up, and then the double phase shift. So it's 1, 2, 3, and then with the one that's going from there. And I think then in total you have an I and a minus I. So I think this is correct. I think the vertical component will cancel out now.
I'm ready to try it. Why did they give us a bomb?
Watch us be completely wrong. Oh wait, but it actually says 12 and a half now. But we need to get 12.
You need to get at least 12. They just put some margin there.
Oh, okay.
Yeah, it doesn't really mean anything.
So the right side is correct. The left side isn't.
So yeah, maybe I can go through that a little bit.
The goal is 12, though. The goal is not 12.5. It says 12.
Sometimes they just do that, like, but
really round.
It's just.
James, can you move the observer to the left place, maybe?
Here?
Yeah.
It's the same, right?
That should be the same.
Because you're observing 1 out of 2 entangled. Not entangled, out of 2. Out of the superposition of, out of one part of the superposition. So the whole thing collapses, right?
I reckon we need to put the phase shifter closer to the left detector. Like as in
Yeah.
the bottom left quadrant somewhere.
You're
Or in-
probably right.
Right? As in we need to shift.
It makes sense, except for this is going down.
I think you need to put, yeah, if you put the phase shifter, yeah,
Or do you want it?
like the bottom left quadrant.
Here?
Yeah, there, or the one above, in between the mirror and the, maybe.
Yeah, can I see what happens if we just take it out? I'm curious.
Yeah.
Let's take it out.
Wait, it still goes down. Why?
Because the momentum from
Just shifted it 1/2.
Oh, but the other detector now doesn't get its 12.5 anymore.
Oh yeah.
Oh.
Why is that?
That's really weird.
This one doesn't get it.
So
Well-
maybe instead of putting the observer at the beginning, we put the observer by the Maxender arms, by the two mirrors. Or do we have to rotate those? No, we don't. No, I don't think we do.
We can't actually rotate anything here.
No, we can.
Oh, we can.
Yeah, but I don't think that's the solution, is it?
Well, you can lose a beam if you rotate it up, right?
That's true.
But then you cannot destructively interfere anymore. So that doesn't help.
This part here is so confusing for me because it goes through it, then it comes back and it gets reflected a second time.
That makes sense because you've got two components.
It's split twice.
However,
So, yeah. This is a big puzzle.
maybe we should put the observer or the phase splitter. Which,
I feel like this is super close to what we had originally, right?
yeah.
What if
So
I
maybe
take
we
this?
have to move the observer.
That's interesting. So this one does mean that the beam that comes down in the end is. Why does that happen? Why is this necessary to have this go 50-50?
Because when the photon hits the third beam splitter, you're going to be shifting. So the beam splitter already shifts it by half a phase. Not half a phase. What am I saying? Yeah, half a phase. So then when it passes through the, what do you call that, phase shifter, you're going to change it by another half phase and then a third time half phase, which cancels out. So I don't know. Do we need the beam splitter? I don't know. I'm confused.
Oh, you know what?
I get why you guys were stuck on this last time. This really is a step up compared to the previous exercises.
Yeah.
Maybe we've already been playing for almost an hour and a half. Maybe we should just take it easy on ourselves and.
Wait, you're talking about giving up?
No, I'm thinking about taking a break.
Okay.
Until next week.
That sounds like giving up.
Okay. Well, Ian's not working tomorrow, so.
Oh, sorry.
You won't be able to stop thinking about it.
God, this is going to be really annoying me throughout the whole workday tomorrow. Let me try. Okay, we can all have a quick brute force.
So if no. We tried a quick brute force last time, and we were trying for like an hour.
Yeah, that didn't work.
So
what did the bomb do again?
the bomb just blows up.
So okay.
We don't want the. We got very close last time though, but I can't remember how.
It always seems like it. So I have one thought. So my question was like, why does this? My question is, why does this affect the result that we get down here, right? Because the photons are all coming in this way, and then in one case they're going split between them, and one they're only going. If we take this out, then I think they all go to the right.
I see your argument.
Wait,
now it works.
No, now it works fine. Okay.
It's when you have the box.
Oh, it's fine. It didn't make any difference.
Huh?
Yeah, see, so it shouldn't make a difference, right?
No, it shouldn't make a difference. Okay.
I think just tried it, right?
No, that was because wait. It doesn't make a difference. Putting it there doesn't make a difference.
Means we have an extra component. Okay, nice.
So we can leave it out. Or we can put it somewhere else, as in maybe further down in the bottom left.
I think if you put it in the bottom left, then probably the direction will change.
Here.
Right?
Yeah.
Yeah, we did that before, and that's what happened.
This time it worked.
Oh my god!
Look at that. No, but that makes sense to me. That there.
Yeah. Isn't that what we tried? Oh, no, we must have tried something. I think the opposite. No.
We were confused.
Yeah.
This is kind of a dead end. This one.
That doesn't do anything. Yeah.
But can somebody now take me through the steps for the top right? Because
here.
Yeah, why did the beam still go to the bottom as a whole without the phase shift?
Well, because the phase shift actually didn't do anything, since you were cancelling the phase shift when you were going upwards and downwards back the same direction.
Oh, it wasn't added twice, it just cancelled out. It was one times plus the phase shift, one times minus the phase shift.
Yeah, because of the direction when it's reflected upwards and then to the top mirror and then back down, you're cancelling it out. So ultimately it's the same as not having it there.
I see. Okay, then I made a calculation mistake also, because in my head I took like twice the phase shift and then cancelled out the vertical component, but apparently that wasn't even necessary, so I made a mistake there.
So what I'm seeing here is that this one has pi. This one that my mouse is over, it has pi over 2, and then now it has pi phase shift. See?
Yeah,
but
that makes
doesn't matter. That doesn't matter for the rest of the circuit.
Yeah.
Yeah, but no, that makes sense, because of course you change direction. So the one that gets reflected to the top gets the phase shift, and the one going straight eventually cancels out, and that doesn't. Yeah.
Okay.
Awesome, we did it, guys.
Yeah.
Yeah.
What do you think would happen? Good job.
Well done, guys. We did it.
If we would change the rock and the observer.
No, but then you would get 25% on the left, right?
Yeah, we wouldn't get enough through. We wouldn't get enough photons through, right?
Yeah, the initial instance would already be, blocked.
Yeah, you get 25%. Yeah. This way. Hey, nice work. So
great.
That's
so this number 17 is number 18 is the last one for interference.
Oh wow.
But it's pretty late, right?
Yeah, it's almost 11.
It's Poor little knight.
We got very far, and I have to say, as far as understanding, I got a lot further than I was last week.
Yay!
Cool.
That
Very
was
nice.
very productive, very fun.
Yeah,
Okay.
I mean, there's only 33 levels.
You can probably get the rest done next time.
So what is varia? I know polarization and entanglement, but varia, what does that mean?
What does varia mean? Is
Yeah.
it like various different problems, or is it variance as in varia as in variance, or
Yeah,
is it? I don't know. I'm trying to think. What else?
Yeah, we'll have to get there. I can't see.
Yeah. I wonder if we'll come across things like, God, what was I forgot all of these. The non-degenerate perturbation theory. Degenerate perturbation theory.
Yeah. I don't think we'll get to the hydrogen atom or something that we
Yeah,
needed.
variational methods. Sorry, yeah, I can't remember what else there was. God, quantum mechanics.
Yeah. So at some point you will get the degenerate states, and then you have some additional interaction that can lift the degeneracy, and then you use perturbation theory to calculate the new states. And that's basically how molecules form. So you have orbitals from two atoms and they overlap, and then you have some perturbation, and then I think they get this discrete energy levels. It's almost something like that. It's a long time ago.
Something like that.
What does a perturbation and a degenerate mean?
Degenerate means just two of the same energy level. And
Yeah.
Pauli exclusion principle. Oh no, wait, that's a different story. Anyways, degenerate means just the same level, and perturbation theory is, I guess it's just something for mathematics. You can take it without considering any physics, but it's an approximation, I think, of what a small interaction does to a system. So, for example, you have many body problems, right? You have the sun and you have the earth. And you can analytically calculate the orbit of the earth around the sun. You just have Kepler's laws, which you can get from Newton's laws. But as soon as you add a third body, you have gravity between sun and the, let's say Mars, Mars and Earth and the sun. Suddenly, you cannot calculate this analytically anymore.
No.
But if you consider the mass of Mars just to be very small and see it as a small perturbation to your already existing system that's analytical, then you can have some calculation about it. But if it's like comparable size, then you have to do simulation and stuff. But this way you can still do it just pen and paper, find an estimation of the solution for your problem.
So it's an approximate solution.
Yeah, but it works quite well.
Have you been watching the three-body problem?
No.
Have you heard of this?
I've heard of it, but I haven't seen it.
There's a whole science fiction series based on what you just talked about.
Oh, that's cool. I had it in the second year of uni for exactly it was an introduction to perturbation theory, and then we had this.
In second year?
Well, it was like the course was called research experiments or something, and then I had one experiment exactly on what we're doing now, like with the setup with lights, and then we had a CSH something experiment, the Bell experiment, but it was with a loophole, so it was still, everything was local. And another one was completely mathematical, where we had to do this many body problem. But
oh wow. No, we learned perturbation theory in third year of uni.
So. Yeah, so for quantum mechanics, we also did it in the third year. Yeah.
But I'm a programmer, so I would just make discrete time step, way to solve it. I wouldn't look for an analytical solution ever.
Yeah,
why do people want analytical solutions to things? You can just write a Python program that breaks it up.
Newton didn't have a computer, so he didn't have the choice, right?
It's true.
Yeah, apparently, which one am I thinking of? Laplace. because Laplace was also really interested in the orbits of planets and moons. Apparently, he just spent a lot of his time with tables, like making tables and tables of calculations over time. And then when he got to be more important in the government, he just had people. He had people to calculate things for him.
That's so funny. No, humans were calculators back then. They had people making those tables, right?
Yeah.
Oh my gosh.
Yeah, we have interns and bachelor students for that now.
Yeah.
Same thing, different times.
Wow.
Well, thanks a lot, guys. This has been super fun. It's fun with 2 people. It's even more fun with 3 people. So I hope we'll do it again.
For sure.
And
Yeah, I had fun.
that's the end
I
of
would
it.
like to be invited another time.
Sure.
Yes, likewise. Thank you very much. And nice to meet you, Nayan, as well.
Yeah,
Thank you
likewise.
for your wisdom.
Thanks, guy.
Great contribution.
Awesome. All right. Well, yeah. See you next time, and have a good night to both of you.
Thank you.
Thanks.
Bye.
Bye-bye.